Hi, everyone. I'm Anna Thomas, working with Azul. I'm going to be talking about lock optimizations for loops in Falcon JIT. So what's Falcon? Falcon is our just-in compiler for Java based on LLVM. We convert Java bytecode into assembly, and the LLVM-based optimizer is inside our running VM. It's also the final tier compiler for Azul's Prime JVM. What this means is we just compile the hottest methods using the LLVM-based compiler. So lock operations in Java are represented using synchronize. So what this means is you lock the object, you perform some operations on the object, and then unlock it. So this is typically a very expensive CPU operation because there is a compare and swap involved. And the second thing is it also limits compiler optimization such as LICM, vectorization, any sort of reordering of instructions, because these locks act as barriers. So the optimization that we are going to focus on is called loop lock coarsening. So on the left side, you see a loop where it runs from 1 to n. And on every iteration of the loop, we are locking an object and doing something with the object. On the right-hand side, we have now coarsened that lock across the loop. What this means is now we are running that lock exactly once. But this has some legality constraints. We cannot do this all the time. So the first thing is, as you can see, y++ is a load and a store operation. And according to the Java memory model, you can move only non-volatile loads and stores, and that too into the critical section and not out of it. So what we are doing on the right-hand side is fine because we are moving it into the critical section. The second thing is we don't know what n is. So if it's like a really long-running loop, you can be synchronizing or you can be coarsening over a very long-running loop, which means you introduce thread contention. So we cannot do that because we need to satisfy certain progress guarantees. So let's see how we do this in our compiler. We start with the same example. We have got the synchronize on the object. In our IR, how we represent this is using abstractions. So we have something that the monitor enter, which is the lock on the object, and the monitor exit, which is the unlock. Abstractions are similar to intrinsics, but they have got an IR body. What this means is we inline these IR bodies at specific points in our custom pipeline. So at the time that we are running this lock optimization, they have not been inlined yet. They are just calls that the optimizer has some idea about the semantics of these calls. So let's see what we do first. We move y++ into the critical section. This means we effectively move the monitor exit to the latch of the loop. The next thing is we introduce something that we call loop chunking. So here we have converted this loop that was originally just one loop into having an inner loop where you have the induction variable j that goes from 0 to chunk size. And also you have the original loop terminating condition as part of the inner loop. And now the body of the outer loop is completely within the inner loop. So you can kind of think of this as, if you had the outer loop and you unrolled that loop by chunk size times, and then you re-roll that loop back. So that's how you get this inner chunked loop. That's what we call a chunk loop. So this is semantically equivalent to the original loop that we had. The next thing that we do is we move the monitor exit to the outer loop header, the monitor enter to the outer loop header, and the monitor exit to the outer loop latch. So this effectively means that now we have coarsened that lock over the chunked loop. So this is how we satisfy the progress guarantee because we know what the chunk size is and we are coarsening exactly across chunk size number of iterations. So until now, we were talking about having a terminating condition, which is kind of simple to analyze. You know what the trip count is at most n. But you can have any sort of unknown exit condition. It can be any expression on I. And the other thing that this chunking gives us is we are converting an unknown exit condition into a loop where we know the max trip count. So we know that it's of chunk size iterations. So what we are talking about is a new approach called loop chunking. We can use it to move expensive operations out of the chunk loop. We have locked it fewer number of times, and the chunk loop can be optimized further with vectorization, for example. We have a couple of use cases downstream as well, where the operation is, if you execute it only every couple of iterations, we can use the same approach. And this is the basis for other techniques that we do over loop chunking. That is it. Thank you. If you have any questions, you can talk to me later. Thank you.